Okay, ladies and gentlemen, let's continue with lecture 14, and I'm going to start, and I'm going to do a problem with you, problem 492. Okay, and I'm going to start here because I would like to explain something, and then I would like to start on that side of the board. So lecture 14, problem 492. Okay. And this problem is a block of ice. A block of ice, 40 millimeters and 40 millimeters, with a height of 60 millimeters in that direction, and it is standing on a table. The ice is standing on the table. Here's the table. Okay. And it is given to us that the ice, that the K value of the ice is equal to 2.22 watts per meter Kelvin. Okay. Forget about the K value. I'm going to get back to that later on, because otherwise we're just going to write it out twice. This problem, except now for the fact that it gives us the K value and the alpha of the ice, tells us that the temperature of the block of ice is at minus 18 degrees Celsius. Minus 18 degrees Celsius. So Ti, the initial temperature, is minus 18 degrees Celsius. The environment is at plus 18 degrees Celsius. So there's a 36 degrees Celsius difference between the two. And then the heat transfer coefficient is given as 12 watts per meter square Kelvin or degree Celsius. Okay. And now it asks us to determine when this block of ice will just start to melt. Okay. Now, that would be when the temperature of one of the corners is equal to 0. So the question is, determine how long it will take for this block of ice to melt. Okay. Now, if we look at this block of ice, if I draw it again like that, only in one dimension, what we see is that on this side we've got the environment temperature and the heat transfer coefficient. Okay. On this side the same, as well as on that side, but we do not have that condition on that surface. Do you agree? What they say in the textbook is it is standing on a table, and you can assume there's no heat transfer through that surface there. Okay. So in terms of, if you think back in terms of the mathematics that we've done with the principle of superposition, one of the requirements was that this boundary condition, or the boundary conditions in terms of the environment temperature and the heat transfer coefficient, must be valid on all the surfaces. And it is not valid on that surface there. So you cannot just start using the equations as given in the textbook. Okay. But we can fix it. We can fix it in the sense that we can say that what is really happening is the following. If we would look at this block of ice, okay, then let's just go back to this one. Let's look at this one. If that is T infinite and H, the heat transfer coefficient, T infinite and H, T infinite and H, T infinite and H. So that is how it should be in the textbook. If you consider this case, then it would mean that the temperature there and the temperature there would be equal. Do you agree? Because of symmetry. We've got the same boundary conditions on this side than on that side. It would also mean that the temperature there, temperature at point 2, would also be equal to that temperature. There's symmetry around that surface there. Okay. You can also do it in the other direction. So if we do it in this direction, then the temperature there, let's call it the temperature at point 3, on both sides would be the same. And on this side also. Okay, do you agree? So over this surface, there's actually a 0 temperature gradient. Okay. So there's a 0 temperature gradient. Okay. You agree? Okay. So how can we fix it? We can fix this problem by saying, well, let's take this block as it is and we double its length. Okay. So where it is 60 millimeters, we consider the problem as if it is 120 millimeters long. If that is the case, then we put that boundary condition on all 4 the sides. And what we're going to have now is that this temperature there and that temperature there is going to be the same. So we've got a 0 gradient over that line there. And we put our coordinate system there. And then we can use the solution. Does that make sense to you? Okay. Okay, so now that we've sorted this out, I would like to start doing the problem, but I need a lot of board space, so I'm going to clean here quickly. Okay, so coming back to the problem, what we're going to do now is we're going to say we've got a block of ice of 40 by 40 millimeters, but now of 120 millimeter high. Kelvin?
Could we also just drop the coordinate systems? Are you given solutions for that in the text?
No, you can't drop the coordinate system. Okay. There's no such solution for that one in the textbook. The one in the textbook is where I think it is something like this. So in that direction, it's an infinite. And then the coordinate system is there. Then you can do it. Okay. So it's a very, very long bar, and then you can do it on that side. Okay. So 40 by 40 by 120, and now let's write down the thermal conductivity, because we're going to use that. Of ice is 2.22 watts per meter Kelvin. Alpha, the thermal diffusivity, is equal to 0.124 multiplied by 10 to the minus 7 square meter per second. The initial temperature of the ice is minus 18 degrees Celsius. The environment is at 18 degrees Celsius, and the heat transfer coefficient is equal to 12 watts per square meter Kelvin. And the problem is, how long will it take for 0 degrees C at one of the corners? And let's choose this corner, and we call it X, the point X. And our coordinate system is now X, Z, and Y. So it is in the center of the block of ice. Okay. So the solution of this, if you go and look at the textbook, is the product of three plane walls. Okay. Something like that, that geometry you get by the superposition of three plane walls. So let's look at the first plane wall. Let's call it plane wall 1. And what we have now is, this is the plane wall, and in terms of the coordinate system, there is Z and X, and that distance is equal to 40 millimeters, which is equal to 2L1, which means that L1 is equal to 20 millimeters. Okay. And the surface where we want the temperature would be on that surface there. Okay. So let's calculate the Biot number. And this is going to be the Biot number for wall 1, which is equal to the heat transfer coefficient, L divided by K. Specifically L1 to indicate it is that wall. The heat transfer coefficient is equal to 12. L is equal to 20 millimeters divided by the thermal conductivity. The thermal conductivity is equal to 2.22, and that is equal to 0.1801. Okay. So therefore, if you look at table 4.2, just get it going. There it is, table 4.2. Take a look for me at the Biot number and see if you can get it. Okay, so you should be able to get lambda 1 is equal to 0.3208, and A1 is equal to 1.0173. Ladies and gentlemen, please. Okay, lambda 1 is equal to 0.3208, and A1 is equal to 1.0173. You can also use the Heisler charts. In this case, we're going to use the calculations to determine, to solve the problem with. Okay, so this is for plane wall 1. Let's now look at plane wall 2. Plane wall 2. Plane wall 2 would be, again, our coordinate system, ZY. Again, this distance is equal to 40 millimeters, which is equal to 2L2, from which we can determine that L2 again is equal to 20 millimeters. Therefore, we can also calculate the Biot number of wall 2, which is equal to, again, the heat transfer coefficient multiplied by L2 divided by K. L1 is equal to L2. The heat transfer coefficients are the same and the thermal conductivity is the same. So we're talking of the same Biot number equal to 0.1801, and therefore lambda 1 is equal to 0.3208, and A1 is equal to 1.0173. And what I forgot to show is that we want the non-dimensionalized temperature on that wall there. Okay. We want the non-dimensionalized temperature on that surface there. Okay, ladies and gentlemen, please, I want to ask you to be more quiet when I lecture. I don't know if I should go faster or slower when you start talking. So I find it very difficult to determine my pace. Plane wall 3. Okay, now we've got the wall in this direction. ZX. And now we are interested in getting the non-dimensionalized temperature on that surface there. That distance is equal to 120 millimeters. So 2 times L, let's call it 3, is equal to 120, from which we can say L3 is equal to 60 millimeters.
So, sir, did you obtain lambda 1 and A1 from interpolation?
Yes, from interpolation.
Wouldn't they be closer towards 0.2?
These two values, 0.18. It must be 0.3 something. You can go and check and make sure if it is better.
0.1081, not 1801 is the two middle digits, 8 and 0.
Sorry, the Biot number should be?
1081, not 1.
Sorry, 1081. Okay, thank you. 1081. Okay. Okay, let's see if I can get this one right. The Biot number for the third wall is equal to the heat transfer coefficient multiplied by L3 divided by K. The heat transfer coefficient again is equal to 12. L is equal to 60 millimeters divided by the thermal conductivity, which is 2.22, and that gives us a Biot number of 0.3243. From which we can determine lambda is equal to 0.5392 and A1 is equal to 1.0482. Is that right? Okay, now the solution, if we put all three these plane walls together, okay, so it means that I take that plane wall and that one in 2 dimensions and do it in 3 dimensions, I can get this type of geometry. So that is where it comes from. So the non-dimensionalized solution of L1, L2 and L3 as a function of time is equal to the non-dimensionalized solution of L1 T, okay, L1, the first wall, multiplied by L2, the second one, as a function of T, multiplied by the non-dimensionalized temperature in the third direction. But if we look at these two solutions of L1 and L2, if we go back to the geometry, what do we see? The same L, both are 20 millimeters, and both give us the same Biot number and lambdas and A value. So we can say that is equal to theta L1T square, okay, multiplied by theta 3 L3T. Okay? Now if we write it out, we can say the non-dimensionalized temperature at point X in the corner minus T infinite divided by the initial temperature minus T infinite is equal to A1 e to the minus lambda 1 square tau cos lambda 1 x divided by L the square of it, because we need two of them. So it is that solution, theta is equal to A1 e to the minus lambda 1 square tau cos lambda 1 x divided by L and square, okay, multiplied by, again, A1 e to the minus lambda 1 square tau cos of lambda 1 x divided by L, like that. And to distinguish the two, because we've got exactly the same here and there, let's put a 1 there to indicate it is for plane wall 1, and we put a 3 there to indicate it is for plane wall 3. Okay. Now something which can be very confusing to students, and many students make this mistake in the test and exams, and therefore I'm going to go very slowly through the following few steps to show to you very clearly what is happening here. Okay, so let's look at this first equation. It is equal to A1 e to the minus lambda 1 square, okay, multiplied by tau. What I'm going to do now is I'm going to indicate this tau, the non-dimensionalized time, as tau 1. And I'm going to explain it to you just now. Multiplied by the cos of lambda 1, okay, lambda 1, multiplied by x. X is going to be on the surface, so it is equal to L1. L1 divided by L1. We're talking of wall 1. Okay, do you agree? Multiplied by A1 e to the minus lambda 1 square, and I'm going to call this tau 2, multiplied by the cos of lambda 1 x is now equal to L3. X is equal to L3 because we wanted the solution on the surface. L3 divided by L, which is the third one, like that. Okay, the two important things is look at tau 1 and tau 2. Okay. What is tau again? Tau is the non-dimensionalized time. So tau is equal to alpha t divided by L square. That is the definition of the non-dimensionalized time. Okay. Let's write it down again. Alpha t divided by L square. Okay. If you look carefully now, you would see that alpha is equal to alpha. It's the same time. okay, that we want to know when the temperature is going to be 0 at the corner, but different L's. So therefore the non-dimensionalized time for both the terms are not the same. The non-dimensionalized time for both the terms are not the same. So that is why we call that tau 1 and this one tau 2. Okay, and that is going to be L1 and that is going to be L3. Okay, so if we write it out, we are going to use it there. It is going to be equal to alpha. Alpha is equal to 0.124 multiplied by 10 to the minus 6 multiplied by t divided by the time, which is 20 millimeters squared for that one. And this one is equal to, again, 0.124 multiplied by 10 to the minus 6 multiplied by t divided by 0.060 squared. Okay, now let's put it back in this equation here. Let's put it back in the equation. And I'm going to do it here. I'm going to say the temperature at point X, we want it to be, the temperature at point X must be equal to 0, minus 18 is the environment temperature. The initial temperature is equal to minus 18 minus the environment temperature, which is 18 degrees Celsius, is equal to A1 of wall 1. So it is equal to 1.0173 1.0173, and then E to the minus lambda 1. Okay, lambda 1 is equal to 0.3208. The square of it multiplied by the non-dimensionalized time, which is that term there, which is equal to 0.124 10 to the minus 6 multiplied by t divided by 0.020 square. Do you agree? Multiplied by the cos, multiplied by the cos of lambda 1, and lambda 1 is equal to 0.3208 multiplied by L1 divided by L1. They cancel, but we must remember it's the square of it, okay, because there are, and I forgot to put it in there. There. Okay. Did I miss something?
So over there, the alpha is to the minus 7. To the minus 7.
Okay, sorry, minus 7. Yeah. Anything else? Everything okay? Okay. Okay, so multiplied by the next term, which is equal to 1.0482 equal to A1, and this A1 is now equal to that term there, multiplied by E to the minus E to the minus lambda 1, and lambda 1 is equal to 0.5392. Square of it, put in brackets there also if you want to, multiplied by alpha, which is equal to 0.124 multiplied by 10 to the minus 7 multiplied by t divided by 0.060 squared multiplied by the cos of lambda 1. Lambda 1 is equal to 0.5392 multiplied by L3 divided by L3, which is equal to 1. And there is our equation. And the only unknown is the time. That's the only unknown. Okay. Are you happy with that? Okay. So you have to be brave and go and solve it. And the answer is equal to 70,020 seconds, which is equal to 19.5 hours. 19.5 hours before the one corner temperature would drop to 0 degrees Celsius. And then it would start melting. Remember, it's at minus 18 degrees Celsius originally. Minus 18 degrees Celsius. Okay. However, there's something that we have to go and do now. Something that we have to go and check. That this is not the final, this is not the end of it. When we use these equations and also the Heisler charts, there's a very important assumption that we've made. And that is that tau, the non-dimensionalized time, should be larger than 0.2. If it's larger than 0.2, then our error of using only one term would be very small. Okay, so we have to go and check that. We've determined the time now, but let's go and determine the non-dimensionalized time. The non-dimensionalized time is equal to alpha t divided by L. Okay, and which one is going to be the smallest? Well, let's see. Let's use the 60 millimeters one. Alpha is equal to 0.124 multiplied by 10 to the minus 7. The time is 70,020 seconds divided by L3, which is equal to 60 millimeters, and that is equal to 0.241. Okay, which means it is larger than 0.2, so we've just made it. If it wasn't the case, it meant that we had to go and take into consideration a second and third term of theta. You can also go and check on tau 1. Okay, tau 1 is there's a factor 3 difference between them. So you can go and check it is equal to 0.723. Unfortunately, that is also larger than 0.2. So the assumption is valid that only the first term approach can be used. Any questions, ladies and gentlemen? Yes. I beg your pardon? If it is less, okay, the question is, what do we do if it is less? If it is less, then we have to go back and remember that theta is actually the sum of n equal 1 to infinite of a1 e to the minus lambda 1 squared tau, etc. So you have to go and calculate it for n equal 1. To get theta 1, you have to go and calculate it for theta for n equal to 2, etc. And you will have to check when this term is starting to become negligible in terms of the rest. Okay. Any other questions, ladies and gentlemen? Yes. Yes. Sorry. Square. That's right. Okay. Any other questions, ladies and gentlemen? Okay.